All right, ladies and gentlemen, here we go, part two of covalent bonding. All the stuff we talked about in the last lecture all led up to this, and this is the reason why we're going to do this. It is because of that we need to figure out why things bond to different things. So the question is, why do atoms of different atoms form covalent bonds? And we'll talk about something simple like HCl. And so, if we do the Lewis dot structure, let me get my pen. Let's go ahead and use it. So hydrogen we know has 1 electron. Chlorine has 7. I'm going to do it this way. It doesn't matter how you do it, as long as you have one unpaired. And of course, we'll talk about these two pairing up and show something like this. These two pair up. We see something like this. And ultimately, we go H bond Cl, because I always like the line indicating 2 electrons, especially if they're between atoms. This is a single covalent bond. Now, what we need to look at is look at the energy levels. Now, this is why I do the energy levels. Chlorine, as we see here, is 1s, 2s, 2p, 3s, 3p. So this is the 3p, and of course, I'm going to put all the electrons in, and this is just for show. Now we're just going to talk about this. And for hydrogen, competitively, the 1s is about right here. This is and this is hard for students to understand. It's like, why, how can these two come in? All of these are so lower than the 1s of hydrogen, and ultimately that we have an electron here. This and this have to line up perfectly in order to interact, to overlap, to form a sigma and sigma star. Well, this is actually a little bit lower here, but this is not drawn to scale, but the difference between here is pretty huge. And the fact this is how this works, and the fact that it's easy to pull hydrogen off of HCl, that's another story entirely. But this is what we're looking at. This is the type of interaction that we need to look at. So I'm going to skip that because I already did it. Carbon is one of these, can form to 4 of the atoms. But let's look at the electron configuration: 1s2, 2s2, 2p2, indicating that if we do the energy diagram, 1s, 2s, 2p, we only have 2 unpaired electrons, not 4. How can carbon, when we look at the Lewis dot structure, can bond to 4 atoms? And it can. And here's the thing, and this is what stumped chemists for a little bit. But ultimately, we did a little bit of mathematics, something called group theory, and we realized that something called hybridization. And so let me move to the next slide. Hybridization is when we take, looking at the second energy level, this is the 2s and the 2p, and chemists realized something, is that both models were right. Here's the thing, that Lewis was looking at things that would be after bonding, while atomic theory was looking at atoms before bonding. And so when atoms decide to bond, I'm giving them personality, but when atoms bond, something happens, is that these four orbitals merge together, and we end up with a hybrid. This is what we call a hybrid orbital. And what happens is the average of, we average these 4 energy levels together. It's a little close to this one, because these are higher than this, so you got 3 of them. But now we have 4 orbitals and 4 electrons, and this is how carbon, now this is carbon, can bind to 4 things and not just 2. And this is why. Now we'll call this hybridization, and then it's the S&P of the highest energy level. will mix. And when we look at these three things, we're looking at an sp3 hybrid. We have 4 sigma bonds. That's where carbon is carbon. Or it's going to be 3 single bonds plus a lone pair. Or some type of combination of single bonds and lone pairs. Now, when we have an sp2 hybrid, that means we have sp2, and then we just have a p orbital by itself, and this p orbital is involved in the double bond. So the p orbital is involved in is used in making the double bond, and so the double bond contains a sigma and a pi, and then we have 2 sigma bonds or 2 single bonds. And then when we have a hybrid, we've got 2 double bonds or a triple and a single bond. So we're looking at something like this. Cyanide, HCN. Those you have a triple bond and a sigma. This is what, and carbon has an sp hybridized orbital. And another way to say this, I'm going to erase all my notation. So if you need to go back, let's go for it. All right, so let's go back to my pen color. So this has 4 electronic regions. And when we talk about electronic region, is a area of electron density. And it's separate from others. So for an sp3, we're talking about 4 electronic regions. sp2, we have 3 electronic regions. sp, we have 2 electronic regions. And this is all around the central atom. Now, why we say this is that now we go to what we call the valence shell electron repulsion theory, or VSEPR. And let me write this out for you. Valence electron pair repulsion theory. And that means when we have, this is a 3-dimensional construct. So we're going to take our 2-dimensional form and make it into 3 dimensions. So the atoms are bonded to a central atom will move to all the bonded electrons are separated by maximum distance, as the atoms will allow it based on the size and shape of the atom. And so what we have is we have, now hold on, I'm going to go back. It didn't like that. So I'm going to come back here, and this is the 3rd time I've done this. And I'm going to do something right now, folks. You see my screen here, so just bear with me. And I'm going to add another slide after this, and I'm going to go from this one. So you're going to bear with me, folks. So we have 2 molecular shape. We've got linear molecules. This is the sp hybrid orbital. So say carbon's in the middle, and hey, I didn't turn on my pen. That's why that happened. So we have a linear molecule, something like carbon, triple bond oxygen. We've got a lone pair, we've got 2 electronic regions. Here's my first one right there, and here's my second. These are the 2 ER, which is electronic regions. Let me write this up here, ER, electronic regions. and this is all around the central atom. sp2 hybrid is trigonal planar in shape, and basically we got 3 electron regions, and this is actually all in 3 dimensions. But this one is actually planar, and here we have the 3 electronic regions. Then we have the tetrahedron, which is an sp3 hybrid. Now I want to show you something in this. So we look at a tetrahedron. Say methane, CH4 is 1, and you notice I'm drawing lines for the 2 hydrogens. Now for the hydrogen that's going back in behind the board or behind the screen, we use a dotted line. And for coming out towards you, we use a triangle. And this is how we draw a 2-dimensional diagram, try and give it a 3-dimensional space. And this is what we call the tetrahedron family. And we're going to go to the next slide, and we're going to do some of these on the next slide. So in the tetrahedron family, we got 3. We have the tetrahedral, which is, I'm going to show you this one. And then we got the trigonal pyramidal. Now the difference between the tetrahedron and the trigonal pyramidal is that the tetrahedral shape, we have 5 atoms, and you got 3 feet, and you got a head, and that's the body. In the trigonal pyramidal, we use nitrogen as my example. We got the 3, we got the body, and the head is gone. It's replaced by a lone pair. We got 4 electronic regions, but the top of this is basically an electron pair, and we don't have any atoms on top of this. So this is what we call trigonal pyramidal. It's a 3-dimensional planar shape. Now bent, this is water, so basically it's nonlinear. It's bent, and we've got 2 electron pairs indicating. I put a circle around it to indicate the electron pair. This is what we call a lone pair, because they're not attached to anything other than this one. There's no atom attached to it. And this is what we call the trigonal planar family, tetrahedral family, and this is bent. I mean, it's in the plane, but it's bent. 3 points aren't make a plane. Now, trigonal planar family is basically like this one, where we got 3 regions and they're all in the plane. So we can draw a triangle, and this is what we call the trigonal pyramidal, trigonal planar, excuse me. Then the other one is going to be bent, and this is when we have something like this, NO2, and we've got a lone pair indicating the 3rd region. See, here's 1, 2, 3 electronic regions, and this is bent because there's nothing on top of here. And lastly is linear. We have CO2, which is 2 electronic regions, and we've got atoms attached to both, or we have cyanide, which is triple bond and a single bond. Again, all of these are linear. And here's the triple bond with a lone pair. Still 2 electronic regions. And this is what we want to talk about. These are the shapes you need to know. There are 2 other shapes, families, that will not be on the test, but I want to let you know what they are, because there's been a change in theory when we were, since I was in college, which happens. It means we're learning things. And it's trigonal bipyramidal, where we have a compound. Oh, let's see. I think this was IF5. It looks something like that. Here's the base of the triangle, and we've got 2 pyramids, so it's trigonal bipyramidal. And then if we take one off, it becomes trigonal pyramidal. So if this one goes away, we have we have a lone pair, and then we got 4 fluorines. There's nothing on the bottom, so we have this trigonal pyramidal, and we have 5 atoms to this, and the 4 of these are in the plane. Then we have the octahedron. Basically, I'm not going to draw this because my artistry is pretty bad. And so this is the end of this lecture. All of this, what you need to know is these know this. Whoops, give me a pen. Know this. Know this. Know this. And we'll talk about this next week. Thank you guys, and have a good day.